So I hope you had a good lunch break. So thank you again for being here. So now I want to talk about a paper and not give a survey. And this paper is a paper about measures of systemic risk. So it's a new approach how to measure these. And that's joint work with Zach Feinstein and Birgit Rudloff. The paper has not been out as a preprint yet. I hope that we finish it within the next few weeks, right? So we have been shifting around a few assumptions and now we need to repolish it, and that sometimes takes time. And of course you can imagine, as you know yourself, right, if 3 guys are involved, then it's also kind of a coordination game, right? You have to play, but that should work pretty soon. Okay, so motivation, of course, I don't have to give here at this program. As you know, financial crisis, they have highlighted the paramount importance of systemic risk, and that is, of course, also related to tremendous cost also to the society. And now the question is, of course, what is, oops, this thing stops. Reason could be.
If you just press on it. Should
press on it? Okay. Okay. Yep. And so what we want to suggest is basically we want to suggest a novel approach to measuring systemic risk. And the idea basically is to provide systemic risk measures that are based on macroprudential objectives, but at the same time enable capital allocation. And then we also present a method for the implementation of that. So the basic idea is that we want to design something which is very similar in spirit to the risk measures I talked about in the morning, right? But now we want to do it on a systemic basis, right? So when we want to do that on the level of the system and not on the level of the individual. And the question is, how can this be done? Of course, I'm not saying that capital regulation is the only thing that can be done in financial markets. Of course, this is not what I'm saying. I'm just saying that we take capital of banks seriously and then use that as a basis for designing a measuring systemic risk. And then this measure of systemic risk can, of course, be used as kind of an indicator in what state the system is, and various instruments can then of course be used in order to change the situation in the financial market. And you can also have all sorts of regulations that is not directly linked to capital, but you can of course also do capital regulation. And so this is a way of providing also a diagnosis to the state of the financial system. So what's the underlying philosophy of the approach that I want to present? The underlying philosophy of the approach is basically described here in this quote. So this quote comes from a paper of Arzner, Delban and Koch-Medina from 2009. But this is already, of course, implicit in this original paper from 1999 of Arzner, Delban, Ebertis, right? And it just says that measuring the risk of a portfolio of assets and liabilities by determining the minimum amount of capital that needs to be added to the portfolio to make the future value acceptable, that has now become a standard in the financial service industry, and that's somehow also the conceptual framework that underlies risk measures, as we've also seen in the morning, capital requirements, right? That's somehow the key to this. And what we will do is we will basically take this philosophic approach seriously and measure systemic risk in terms of individual capital charges. The difference now to the standard univariate theory of risk measures is that we do not take the capital of a single firm as the asset in which we measure risk. But what we do instead is we have a system of banks, right? And then we take as eligible assets the capital allocated to each of the banks. So we take a multivariate approach because we have a system of banks, like say n banks, right? We also have n places where we can place capital, right? And then the amount of capital you add to these n banks will of course change the dynamics of the financial system. And that will somehow be randomly, some random outcome will of course appear in the end. And then what we check is whether or not this random outcome at the end is acceptable from the point of the view of the regulator. So that's the idea behind it. So it will be a multivariate approach taking this serious. So here's the outline of the talk. So what do I want to do? First, I want to present measures of systemic risk, provide the general definition and properties, and then I will introduce a derived concept that we call auth and risk measures. So auth and risk measures are a conservative simplification, and these auth and risk measures, they also exclude certain externalities of capital levels that are included here in our systemic risk measure. What's the problem? The problem is, if you look at the macroprudential objectives of a regulator, and the regulator basically looks at the impact of the financial sector on the whole society, right? Then, of course, you can regulate the individual banks, for example, by imposing capital charges to the individual bank. Now, it could, of course, be the case that if you impose a very high capital charge to one of the banks, right, then in order to to be sure that the outcome is acceptable, it might be sufficient to just add a low capital charge to some other bank. While if you add a medium-sized capital charge to the first bank, it might be necessary to impose a larger capital charge on the second bank, right? So there is some interaction, there are externalities, and these externalities are actually picked up in the definition of the risk measure, and then for practical purposes one could also ask the question, how can one come up with a more conservative, simplified concept that excludes basically these externalities in capital regulation. Then the next thing is, I also want to present a grid search algorithm that basically explains how these things can be computed, and then I want to present some numerical examples. Probably I'll do that today, if time permits. If not, I'll do that tomorrow. So the numerical examples will be based on network models. Probably most of you know this Eisenberg-Noé paper, right? This is a famous seminal paper from 2001, and management science has been extended in various directions. And so we will base the analysis in the case studies on this model and also on this model here, Cifuentes, Shin, Ferrucci. This has also been picked up by Amini, Filipovic, Minka, Chen, Liu, and Yao. They basically provide a more detailed mathematical analysis of this approach. The model is basically due to these guys. Tomorrow I will actually present this paper. So this paper is a paper that integrates all these models in one model, right? And you can have all the facts at the same time. So that's what I present tomorrow here. Okay, so measures of systemic risk. As I already said, we basically identify risk with capital requirements. What's the reason behind it? Well, if you measure risk, you need to have some scale on which you measure risk, right? And so one typical approach for measuring firms of risk of firms is to look at cash, right? Cash that needs to be added to make something acceptable, a firm acceptable. And so we want to also follow this philosophy that we basically impose this translation property, and that means that basically risk and capital requirements are somehow identified. So that defines the scale on which risk is measured. So this philosophy requires basically three ingredients. So the first ingredient you need is a notion of acceptability. You need an eligible asset. So the eligible asset is basically the asset in which you are allowed to invest your supporting capital. Right? That's the second thing you need. And the third thing you need is you need a model of the economy or a model of the financial sector. So it tells you conditional on banks having a certain amount of capital and conditional on certain risk factors, what happens to the economy, what comes out of it, right? And so that are the three ingredients. And here, in this case, of course, the notion of acceptability, which you want to have for macroprudential regulations, that should be some kind of an overall criterion set by the regulator or the government, right? That's usually what it is. And what it is, of course, is something which is debatable, but that's basically somehow the idea behind it. And the eligible asset, as I already mentioned, what we take here will be the capital of these N banks, right? And here we make certain assumptions in the case studies, how we model basically the financial system, but that's completely flexible. You can also use more complicated model. For example, I know that Ms. Borovkova gave a talk here, right? So she's looking at more complicated models, these models, simulation models, and models like this could also be used. So basically, as I mean, a very simple picture here. So what's a simple picture? The simple picture is you have somehow a system of banks, and you add to this system of banks capital, right? So that's what it is. Then conditional on what the banks, how the banks are endowed with capital, and conditional on some random factors, you have basically here something like a model, right? A model of the economy, right, or the financial economy. So that's what we have. So that's capital, and then here there's some outcome, and you want to check if this is somehow in an acceptance set or not in an acceptance set. This is just the basic idea, right? So that is ingredients. And now the basic idea is that basically the regulator gives the acceptance set to you. The regulator tells you what needs to lie in the acceptance set, what kind of random variable needs to lie in the acceptance set, what kind of measure the regulator uses. Like, for example, cash flows to the society or cash flows from the society or something like this. The regulator can give you the model of the economy, so they can decide it themselves. And then capital is allocated here, conditional on the capital, you compute what comes out of it. Then the regulator can check whether or not it's okay. And then what you do is basically in this banking system, you collect all the multivariate capital vectors here. So let's say we have here two banks. This is the bank 1, bank 2, capital of bank 1, capital of bank 2. And what comes out of is there are then, of course, combinations of capital of bank 1 and capital of bank 2, such that if you start with that and run that through your model, some acceptable random outcome comes from that. This is the basic idea. And this can be given by the regulator, this can be given by the regulator, right? They can choose whatever they think is appropriate. And what we do is basically just suggest a conceptual framework, right? So it's not really deep mathematics, it's more about suggesting a conceptual framework, how to do that. Okay, so here are the ingredients of the model now formalized a little bit more in detail. So we have financial firms, that are those guys up here, N guys, and we have a vector of capital endowments. So each firm has a certain capital, so these are just real numbers, K1, K2, Kn, right? And each of these capital endowments plays basically the role of capital of individual banks in the general theory of risk measures, usually. But here we have a multivariate setting, of course, because we have n banks. And then the idea is that there are certain sources of risk. Risk comes here from some randomness, right? Randomness is in the system. What could randomness be? Randomness could be what is somehow the cash endowment of the banks initially, that is maybe due to certain investments the banks make, right, which are outside of the banking system, right, or also inside the financial system, but not directly related to the direct liabilities the banks have to each other. That could be some risk. You could have also certain illiquid assets which have certain prices, and there are a lot of random effects. So for this reason, we introduce here random vectors x and s, and these random vectors x and s, they are supposed to model the sources of risk in this model. And then the idea here, in a simplified version of the model, you can do that more complicated if you want, is that banks, if they have this capital endowment here, that they have basically an amount in liquid assets, which is k plus this random vector s, and an amount in illiquid assets, or if you take here other dimensions, some other random parameters which impact the situation of the banks, that is encoded by this S. So that's basically just the basic idea.
But why you add capital to liquid assets?
Yeah, I mean, the basic idea is, I mean, this is just a simplification. You can do that much more complicated. But the idea basically now is the following. We later see that in examples. The general framework I wrote down could be written down more complex, of course, mathematically. We didn't want to write it down too complex to make it not too abstract in the paper. And so the idea basically is we assume we have banks. The banks have external assets. So they have a liquid asset, which is kind of a cash asset, right? They have illiquid assets, right? Which are also traded in the market and there can be price impact, right? And then the banks, on top of that, they also interact with each other through direct liabilities, which they have to each other. There can be also cross-holdings, bankruptcy costs, you name it. There can be a lot of stuff. But the basic idea of the model is that we, later on, model the randomness through the endowments of the banks. So what is the endowment of the banks? The endowment of the bank is what they have in the cash asset and what they have in the liquid asset, right? And this randomness is modeled by X and S. And now the idea is that in addition to this random endowment which they have, right, they have also a deterministic amount, yeah, which can be put into this endowment in addition to what the randomness triggers. And this is somehow what we interpret as somehow the basic capital, which is added to the endowment.
Capital is not cash.
Yeah, of course. I mean, you are completely right. In general, that is not cash. This is just the way we set up the model, right? So the idea of the model is just, it's of course simplified, right? The model is, we have two types of external assets.
I mean, for example, when you look at capital regulation, when you
Yes.
say that the bank has to have 8% of risk-weighted assets
Yes.
as capital, nobody means that they have to have 8% of their assets in cash.
No,
No bank has
I know,
8%
yeah.
in cash.
Yeah,
Yeah,
I mean,
but
you have
1% in cash.
these different tiers of the capital, and then you basically have to check whether that's all fulfilled, and then you have certain weights that are added on that and stuff like this. That's completely right what you say. Of course, it's completely right. This is kind of abstracting from the very specific structure of the way how this is really implemented in practice. The basic idea is basically you have a bank. The bank has a kind of a pot of endowment, right? And this endowment evolves over the period of one time unit, and the
No, I
outcome
understand.
is
Like
random.
In your first talk,
Hmm?
you didn't distinguish liquid and illiquid. So there,
No.
you
No.
just add to the portfolio some
Yes.
cash. But
Yeah.
here, because you insist on distinguishing the liquid and
Yeah.
the illiquid, then logically you should not say that the capital is only constituted of liquid assets. I mean, there's no such rule. Because otherwise, capital regulation and liquidity regulation
Yes.
would be the same problem, but they're not.
Okay, you're of course right. The idea basically is just that we want to set up here a notation that is consistent with the numerical examples which we want to do later on, right? And for this reason, it's just convenient to split the endowment of the bank into two parts, right? And then it's just the convention that we use here, right? That we say X and S are random vectors, or for each bank they are random variables, right? And they are fixed. And then what we check is, we check what happens to the outcome if we can add in addition a deterministic number to the first component of this two, right? This is just what we do, right? So you're of course completely right that one should not claim, right, that this is the only way how capital should be interpreted. It is instead a very specific abstract modeling structure, we assume, right? Just in order to be able to write that down easily, right? This is what we do. So this is just the reason why we do it like this. So K is the amount of capital in which we want to measure risk, it is added to something which is random, and we can also have additional random effects in some other part of the portfolio, which are allowed here, right? This is just the idea. And this random shock now, that refers only to the primary evolution of assets due to core business activities and systematic risk factors. This is the primary thing. But on top of this, you can now have, of course, a financial network, like the Eisenberg-Noem network, right? So what is the Eisenberg-Noem network? Probably most of you have seen the paper. I'll also explain it later on, but there the idea is you have a banking system, and the banks have bilateral contracts, so they have liabilities to each other, right? And so then at the end of this time period, they have somehow this random endowment now, right? And now at the end of the time period, they have to fill the obligations, right, to each other, right? So the problem which occurs now is that, of course, the amount of money I have to fulfill my obligation depends on whether or not the other guys fulfill their obligations, and also to what extent, right? So you have an equilibrium problem, right? You have an equilibrium problem because the payments you make depend on all the payments the others make, and vice versa, right? So it's a complete natural equilibrium problem. And so that's the reason why, on top of this randomness stuff, which is very simple, this randomness stuff, this is kind of the classical setting, we put here a second function, which is a function e, which maps this k plus s x to some outcome. And it does this pass by pass, right? Pass by pass, so scenario by scenario, right? So we have random endowments to each of the bank, right? That's the x and the s, right? Random endowment. And then we have some clearing process, and that gives us scenario by scenario payment, right? From one bank to the other, from the banks to the outside, and stuff like this. So on this level, it's quite abstract. It's just a function, right? It's just a function. And the function is, of course, a vector. And we interpret these components. I'll make it more concrete later on. The components E1 to En we interpret as the equity and losses, the random equity and losses after clearing. And E0 is interpreted as the cash flows, or let's say the wealth of the real economy after clearing, right? This is how this is interpreted. I make an example later on, right? Then it's maybe clearer, hopefully. But that's the mechanism. So the mechanism is we have initial randomness in the endowments, then we have complicated clearing mechanisms in a system of banks, right? And then something comes out of it to the economy. And the reason why we set up this formalism, maybe it's hard to see it at this point, why we exactly set up the formalism in this way, that the formalism, as we set it up here, covers all these models, right? That's the reason why we do it like this. All the models can easily be written in this form, right? This is the reason. Okay, so let's see again what we have. We have the eligible assets. Then we have terminal wealth here of the real economy. That's the zero component. And then we have terminal wealth of the banks, right? So that's a cash flow and random evolution model in the middle, right? So that's how it works. And then the idea is basically the following. The zero component gives us the random cash flows or the wealth of the real economy, right? And now the regulator says, okay, I now check whether or not this random variable lies in an accepted set of some classical risk measure, which is the one I want to use as a regulator, right? That's somehow it's set up, yeah.
I didn't understand how you map the E1 to ENs from all the banks to E0 of the society.
Yeah. I have that later here on one slide. Maybe it's hard to understand if one doesn't make that concrete in the beginning. So the model which we use here for illustration later, maybe I should do that model now and then go back to the abstract framework. The model which we use now is the model by Eisenberg-Noem, Cifuentes, and mathematically extended by Mina and Minka. So the idea is basically that you have a system of banks, right? So you have a system of banks that are the banks. So that's basically your financial economy, and you have an outside node. The outside node, that's a real economy, right? And now these guys, you're inside the system, they have some liabilities to each other, but they also have liabilities to this outside node, which is the real economy. And the outside node might also be required to cover some of the losses that occur inside the system, for example, to bail out banks if the financial system is in trouble. So that's basically the structure you have, right? Here's a zero node, and you have all these other banks that are floating around. And so one model you could imagine, it's just one model. The framework is much more abstract, right? But you could have one model, which is this Eisenberg-Noe model, which is basically this model with these nominal liabilities. So that's a matrix, and P bar ij denotes the liability bank I has to bank J, right? This is something bank I needs to pay to bank J at time 1, right? But of course, there could also be defaults, right? And if there are defaults, you have to compute how much of this amount is paid actually to the bank if it's not the full amount, right? And so that's endogenous in the model. So if you compute the total liability of bank I, you have to sum up these liabilities of all the banks, and you receive that. What you can do then is you can compute the relative liabilities of all the banks, and that are, of course, the liabilities to each of the banks divided by the total liabilities the bank has, right? So this is the liability of bank I to bank J divided by the total liabilities bank I has, right? And so another ingredient we assume is an inverse demand function.
How do you get the liability of the bank to the society then?
Yeah, here's a zero node. That's also included here, right? So you also have liabilities to node 0, right? 0 is a society.
But between banks, you know, the bank in an interbank network, each bank knows how much its exposure or how much it's lent to one bank.
Yes.
So you can write that number down. But what is E0? What is the...
It's deposits. Deposits.
Yes.
People deposit in the bank, so the bank holds them.
So it's basically just, as Rama said, the relations between the banks and entities outside the banking system, right? Like deposits or debts given to the outside, something like this, right? And that's aggregated here. So we assume that's all in one node, right? We don't distinguish that many agents. We could, but this is not done. And so this is what it is. And we also assume that we have an inverse demand function on illiquid asset. And now the idea is that in this system, the banks have endowment. Endowment consists of the liquid part and the illiquid part. And the illiquid part, right, has a price that's governed by the inverse demand function, right? And so then the model works like this. The obligations must be fulfilled at the end of the period via transfers of the liquid asset. And the illiquid position usually is not touched. But if you don't have enough assets of your liquid asset, then you have to sell some of your illiquid asset in order to fill your obligations. But the problem is that the illiquid asset is subject to price impact, right? This is modeled by this inverse demand function. And since the illiquid asset is subject to price impact, of course, the price of the illiquid asset will diminish if you need to sell it. And it will not only be diminished by the amount you sell yourself, but also by the amount the other guys sell, right? So there is global interaction. So you have local interactions through these direct liabilities that need to be fulfilled in an equilibrium. And you have, at the same time, global interaction through the price of the illiquid asset. Right? It's market interaction, right?
Then if you have an equilibrium, why do you need to postulate the inverse demand function? In an equilibrium model, the inverse demand function is determined by equilibrium.
You're right. It depends really on what level you set up the model. I mean, if you have a model, of course, you have different levels of endogeneity you can implement in a model, right? You can have a kind of a full-fledged, very complicated model in which many quantities are endogenous and only some are exogenous, so you have mechanisms that also derive, for example, price as a function of quantity. Here we don't do that. The model is not that complicated. The model assumes that the relationship between quantity and price for the illiquid asset is exogenously fixed, right? And in equilibrium, what we compute is given this inverse demand function and the model, we compute then the equilibrium clearing vector and the equilibrium price of the liquid asset. So that's the equilibrium we take. I have the fixed point equations on the next slide. That's the fixed point problem you get in the Cifuentes model. So these are the clearing payment vectors the banks make. So bank I pays a total of that. And the x and the s parameters, that are the parameters that were randomly sampled in the beginning, right? And if we have capital K in there, then we would have here a k plus x, not an x, right? Yeah. Okay. So how does it work? What is the total payment bank I makes to the other guys in the society, right? What's the total payment it makes? If the bank has enough money, it just pays out what's supposed to pay out, what is promised, right? If the bank doesn't have enough money, then it needs to pay out everything what it has. It's a default, right? Everything the bank has will go to the obligors. And how will it go to the obligors? We assume that it goes to the obligors proportional to the original liabilities. So that's why we took this.
So this is a model for a payment system.
Yes.
So actually, Eisenberg and Noe never say the word capital in their whole paper. This word doesn't appear because it was really designed to model a payment system where it's like, you deposit a check in bank A, it's a check drawn on bank B.
Yes.
So at midnight, bank B, looks at all the flows and so. So this system has to clear every day at midnight. So all the cash flows need to be sent. If you cannot pay the cash, you default. This is how the payment system works. So it's exactly like this.
Exactly. That's the model.
But it's not about capital requirements because capital isn't cash. And if you look at, so this is really every day at midnight you have to clear the payments because they're all short-term payments. But for example, if I have a 30-year bond in my portfolio, I don't have to pay back tomorrow anybody. So there's no cash flow.
Yeah, you're completely right. But the point what we make here is this is just an illustration.
I mean, this is not a remark on your paper specifically because there's a lot of paper who use this model as a model for insolvency and capital requirements. And it is fundamentally not about that because it's about cash flows because you liquidate at time one. And these are really cash flows. You use the word cash flow correctly because this is about that.
Right, but I think it's still not somehow problematic in the respect how we use it. I mean, the basic idea is just the following. I mean, basically the model we use is also not really important for the conceptual approach we make. It's just for illustration. But why do we use the Eisenberg-Noe model? The basic idea is just that for simplicity, that's kind of the easiest thing you do is you assume you have a banking sector, right, which just lives for one period, right? This is what you look at.
Okay.
And then this is a model. This is a model. No, this is just a model we use for illustration. It's just for illustration. Very simple illustration. And then in this banking sector, which just lives for one period, the idea is that we have a network. We have complicated obligations to each other. And then we just play a one-period game. The one-period game basically is how do we clear the stuff at the end of the day or the period or the life of this economy. And then since we just look over the time horizon of one period at this stage, right? We just ask the question, how much cash, now interpreted as a very simplified version of capital, do we have to need to add to each of these entities that the outcome of this period that lives just over one time step is okay. This is just what we do for illustration, right? It's just for illustration. And the good thing about this example is, that's the reason why we use the Eisenberg-Noé and Cifuentes model, is that it is a certain model that allows really to derive in a one-period model the clearing of liabilities that, of course, cause payments that depend on each other. That's the reason we do that, right? So it's just for illustration. So how does the model work? So if the bank cannot pay everything out, what it's supposed to pay, how much does it pay out? So bank I receives, of course, payments from the other guys. That are the payments the other banks make, and bank I receives a proportion of that that's supposed to get, that was stored in this A matrix. The bank has also some cash floating around, right? And the bank has some illiquid assets, and the value of these illiquid assets is given by the amount it has times the price of the liquid asset. So how is the price of the liquid asset given? The price of the liquid asset is given here. In order to get the price of the liquid asset, you have to sum up the amount of the liquid asset that is totally sold in the market. How is that computed? Well, the bank is supposed to pay P bar I, and so if it has enough assets, it has to do it. So we subtract from PI bar the XI, which is the cash amount it has, and we subtract the sum of the payment the bank receives from the other guys, right? And once we've done that, the remaining amount, right, is the residual obligation that remains to the bank after using up the cash resources and the payments it gets from the other banks. And so this is the amount that the bank needs to generate by selling the liquid asset, if it can. So if it can, then this is the cash amount it has to generate by selling the liquid asset. So how many liquid asset does it have to sell? You have to divide it by the price, yeah? To divide it by the price, then you get the amount of shares you need to sell. But of course you can only do that if that is less than the amount of illiquid assets you have. That's the reason why there is a minimum, right? Yeah? If this is more than you have, right, then of course you can only sell what you have, right? And so if you sum that up and plug that into the F, the inverse demand function, you get the price of the liquid asset. And P0x, that is what the society is actually fulfilling. The society never defaults, is the assumption here in our toy model example. That's the reason why we have that. And so given an x, given an s, we have to solve this fixed point system for the pi and the pi. That's what we have to do. And that's equilibrium. That's a Cifuentes-Ferrucci equilibrium generalizing. Eisenberg-Noé. Eisenberg-Noé doesn't have this equation, right? And not this. There's a difference, right? Eisenberg-Noé is just this without this. And if you add an illiquid asset, you get in addition this equation and this term, right? That's the difference. So that's the model. And if you have that model, you have clearing. And so what are the EIs now? The EIs are the amount you receive from the other banks, plus the cash you have, plus the value of your liquid assets in equilibrium, yeah, minus the obligations you have to fulfill. So the EIs are now positive, so they're your equity, if this is positive, and if this is negative, then this is exactly the damage you cause to the system, right? That's what it is. The losses you cause to the system. That's what it is. So that's the model we use for illustration. And you can actually formalize this model in this manner, right? That's the reason why we do it like this, right? Also, more general models can be formalized in this manner, but that's the reason why we set it up like this. With the eligible asset, you have this randomness, then you have some function of the system, right? Two final payments or final final equity and losses, right? That's what it is. This is just a function, right? The function is given through the clearing mechanism, right? That's what determines the E. And then we have this acceptance set. And now the idea of the systemic risk measure is just, as I mentioned before, down below here, that the systemic risk is just the collection of all these K vectors, all these capital endowments of the banks, such that if you put that through the system, at the end you end up at a random variable that lies in your acceptance set of some monetary risk measure like the ones in the morning, right? So it could be VAR, it could be AVAR, it could be utility based short for risk. The regulator just says we have a banking system that generates some random cash flows to the economy outside, right? Some random outcome, some random variable, and now we say certain random variables are okay for us, certain are not, and you have to have enough capital, quotes and quotes, capital in the system that the random variable that is paid out to us, that affects us, is in this acceptance set, right? So that's basically the idea behind the whole concept.
So this is more like deposit insurance.
Well,
Because E0 lends to the banks. It doesn't borrow from them.
Not necessarily, they can have credit, don't they? Like,
No, but not in this model.
I mean, like, in general.
no, in this
No, I'm not
model,
talking about general, I'm talking about this. In
Yeah.
this model, E0 only lends to the banks.
why? In this model, it's possible to do everything. E0 is completely general somehow. It's just a function. It's a function that takes basically the financial system as input. So you have a function that depends on the random endowments of these guys in the system. Say of these n vector.
How is E0 computed here? I didn't get it.
E0 has a following property. It needs to be a measurable function which is increasing and concave. That's it.
That's it?
That's it.
So why can I call it systemic risk?
Yeah, the idea basically is just you have your system of banks, you have your zero node, and then here these guys, they have certain assets and liabilities. They have external assets, and they have, of course, inside the banking system liabilities, and they own also parts of the banking system.
So
And
it's,
there are also payments to the outside and
M
payments
is
from
what-
the outside.
What's M?
Hmm?
What's M here?
Yeah, M is just the random vector that parameterizes, basically, in the example, this liquid asset amount, right?
M?
M is a dimension.
Okay, and N is the number.
M
of-
is the number of banks.
So why are M and N different?
In general, they are allowed to be different. In the example, they're the same. Right?
Okay, so the key ingredient is the function E0. How do you define it?
Right. Yeah,
So-
and so one example would be to use Eisenberg-Noyes, if we end this Amini, Minka, these models, they can be used in order to define the E0. That's what these models do. They do not do anything else, basically, but defining an E.
What do they do?
That's what they do in the end. That's what the model is. They have a model,
Yeah.
they compute an equilibrium, and the equilibrium gives you the E function. That's what they do. Of course, then you can analyze the model. I'm not saying that you cannot do anything with the models. That's not the point. The point is that the models, right, in the end, generate you an answer to how the cash moves around in the end. And at what wealth level the entities in the system end up. That's what these models do.
Yeah, so.
And that can be formalized by such
Okay, so you take a
E
network
function.
model,
E0
you
is
take
only.
Eisenberg-Noyes,
Yes,
and then you compute the clearing factor.
yes,
The clearing factor key gives you after the clearing is done,
yes,
what's left in each node.
exactly.
E0, E1, E2, so on. And then you only take E0. Why?
Yeah, you can do it differently. It's completely flexible in this approach. It doesn't rely on E0. The mathematics we do here go through, if you want to do it more generally, it's possible, no problem. But the idea was we didn't want to write it up initially in a multivariate setting. So the idea was just that you model the society as one node, the zero node, right? The outside economy, that's the idea. And the idea was that the regulator imposes acceptability on the level of the society and not of the level of the banking sector. So the banking sector is just in this formalization understood as an instrument for facilitating the wealth, the overall wealth of the society. This is just how it's done here. And then if you do it like this, if you just care about one node, right, then you have a univariate formulation. Then you have this zero function, which is the term related to the real economy, and then you just check whether or not this is an A. But of course, you could also do it multivariately. But then you need acceptance sets, which are also acceptance sets of multivariate random vectors, right? And then you cannot use the standard risk measures anymore, which you use like bar, A bar, stuff like this. If you set it up like this and say the zero node is the only one we care about, then this can be written like this. The point is, what we do here is not like Brunnermeier and Cheredito, right? They don't have any network effects in there. They have basically these X variables, which we have, and sum them up. That's all they do, right? And what we have is we have here a model in which you can also incorporate all sorts of interaction, if you want to. Right? Basically all the stuff which is in this network models can be implemented into this.
Yeah, but
Notation.
you're also summing them up because you consider there's only one node called zero, which is equivalent to summing up the losses of all depositors.
Yes, but the difference is zero is not summing up anything which is in the X and the S. It is derived through a clearing mechanisms that takes X and the S as given. So the E0 will typically be a nonlinear function of the X and the S, right? And this is in contrast to Brunnermeier and Cheredito. They just take an X and sum it up, and that's it, right? Here, the E0 is endogenously derived from the model. It's usually not linear, right? In the X and the S, right? So this is basically the idea. I mean, the basic concept is just take a counterfactual model. Assume you have something initially, you put it through the model, right? And then you have some outcome, a random outcome. And then you wanted to control that random outcome. And as a regulator, you just are interested in this 0-1 decision, whether or not you find it okay, right? And so you have your acceptance set. And the idea is basically to say we measure capital in terms of the capital that needs to be put in here in the beginning, such that if we run the model, there is a random outcome that lies in the acceptance set the regulator gives. This is the only idea, basically, right? So it's rather simple, right? And the fact that we do it here one-dimensionally, this is just because we don't want to do it too complicated. So if we do that, the risk measure which we get has certain properties. So it's a set-valued risk measure. This is also what I indicated here. And the set-valued risk measure has now the property that it has, again, the translation property. That's how we define it. So if you add k euros to the banks, right, then the set of acceptable capital requirements is exactly shifted by this vector, right? So risk is again measured on a monetary scale. That's what we have here. We also have monotonicity here written with these sets. So if y and x are the random vectors governing the system, governing the endowments of the banks, and the banks have randomly more endowment with x than with y, then it means that there are more capital vectors that are acceptable, right? This set than in the case in which y is worse. This is the monotonicity of the risk measure. Now just formulated with sets, right? Yeah. You can also formalize convexity and things like this, and the interpretation of these objects is completely like in the scalar case, right? There's no difference here. So I don't have much time here, so maybe I skip the Olsen risk measures. I also have here Brunnermeier-Scheredito, which are a simple special case of our approach. They're not really the same because they don't measure risk multivariately. What they do, that's what Rama described. So what they do is they assume banks course externalities, we sum them up, right? We add the externalities to GDP, right? And then we see how much cash do we have to, or how much capital do we have to add to GDP plus externalities, so that becomes acceptable. That's what they do. And they use a utility-based short-term risk measure in order to do that. So they also have a special structure how they set that up, right? That's what they do, and that's it. And then afterwards, they computed this overall amount. They then allocate it to the individual banks in the second step, right? The difference to what they do is that in our case, we have a much more general approach, and the approach also is not looking at some cash you have to add at the level of GDP. What you really look at is you take the capital of the banks, given the capital conditional on that, you compute what happens to the economy, even if you have networks and liabilities and aside the economy and clearing, and then what the outcome is. And so it turns out that there is a way to relate their approach to our approach through this concept of Olsen risk measures that I cannot explain anymore because I promised not to go over time this time. Anyway, we have an algorithm to compute it, but maybe I should go to the example. Maybe that's best, right? Hopefully that makes it also clearer what's going on here. So we have this Eisenberg-Noe-Cifuentes model. I already explained it. It's this liability matrix here. So a system like this, and then these are the clearing equations. I already explained that in the beginning. And now what you do is you can do some case studies. And one case study we did was a case study with only local interaction in the network. So this is a case study where we have an Eisenberg-Noe model, right? And in the Eisenberg-Noe model, we just have these local liabilities that need to clear in the end. So how do we set up the model? We use tiered graphs in order to generate the network, right? So how do we do that? We have a mechanism that generates randomly the connections between individual entities. Tomorrow I'll explain that more carefully how you can do that. And then after you generate these links, you put a fixed number to the link. That's how it works. And so that's what we've done here. And in a tiered graph, you have different groups of agents. So in this case, we have here 2 tiers and 2 groups. Few firms with large obligations, many firms with small obligations. And so randomly, we generate the links within the groups and between the groups, and then assign the obligations to it. So that's how the model is generated. Then we have a further ingredient. The further ingredient is this X vector I mentioned, right? So that's random endowment of the individual bands, right? That's samples, it's a random vector. And then we also have to say what is the acceptance set. And we define here, for example, the acceptance set by A1. That's possible. So what are the ingredients? The ingredients is, how do I set up the network? Ingredient 1. How do I endow the banks with some cash initially? So we do that with a multivariate vector. Here we used beta distributions in order to do that, just because they're bound support. Just for simplicity, you can use whatever you want, right? It doesn't really matter. You have to add a dependent structure between the components and stuff like this. So you can use some copula, whatever. That's what we did here. And then we do comparative statics. We vary the degree of connectedness, right? And so this is what comes out of this case study. Here you have group 1, and you can compute the capital requirements, and group 2 capital requirements, and then you can display the sets of acceptable capital requirements, the combinations here of capital requirements for group 2 and for group 1. And for each of these different scenarios we consider, right, different degrees of connectedness, we get different sets. That's what we get. And the trade-off is also completely clear. So you see if the connectedness of the graph changes, then of course the combinations of capitals that are okay in this model, they also change a lot. And so you see that these sets here, which you have here, the black set, the blue set, so the sets are always upper sets, so like this, they move around. You can, of course, also look at networks with local interaction and global interaction. That means we have now also this price impact here due to the Cifuentes model. And there we can, of course, again, come up with random mechanism, a tiered graph that computes the connections and the liabilities of the bank to each others. You can also then, of course, introduce price impacts to an inverse demand function. You need to sample the endowments of the banks randomly, right? Yeah, so liquid parts, illiquid parts, that's the X vector and the S vector. You do that, and then you need to specify your risk measure. Here we use the entropic risk measure, and now we vary the fraction is a liquid asset. So that's what we do in this case study. And here you see, of course, that if you vary the fraction of the liquid asset and increase the fraction in the liquid asset, then the capital constraints become more conservative, which means that here the boundaries move up, right? That means you have less combinations of less capital vectors, right? Which are okay given your acceptance criteria in this model, right? So that's what this picture here shows. And so what's the conclusion? So what we did is we had a very simple methodology to define systemic risk measures. The idea is just you put capital at the beginning, you have some model, right, that tells you what comes out of it. At the end, including randomness, you have an acceptance criterion, and then given this model, you just collect all the capital vectors that lead to an acceptable random outcome. That's what you do. It's very simple. And that can include all sorts of economies. So we illustrated, just for example, using the Cifuentes model and the Eisenberg-Noé model, that these models, the one featuring only local interaction, the other featuring local and global interaction, they can easily be integrated into this framework, and you can do numerical case studies with that. What we did not do, due to lack of time, is to present a pragmatic approach for the implementation in practice. And that's something one can also do to make it simpler. And we have algorithms, of course, also to implement it. But what I showed is that it's actually easy to implement this approach in toy case studies. And it gives you somehow a multivariate view of risk, right? And you really see the trade-off in terms of capital you have between the various banks. The definition of the systemic risk measure is also capturing a really, in an operational way, how you can control the systemic risk. So I think it is a good tool for the diagnosis of systemic risk. Right? Okay, so thank you very much for your attention. I think this time I finished up the one.